Hello everyone, I am Dr. Janavi Chakravarti, Assistant Professor, Department of Mathematics, Bardhaman College of Engineering. Today in this video, I am going to discuss how to find numerical solution of first order ordinary differential equation using Euler's method. Now let us see what is Euler's method. First of all, we need to consider first order ordinary differential equation which is of the form dy by dx is equal to f of x comma y, and the initial condition is given as y at x naught is equal to y naught. To solve this equation means we need to find y of x. To find y of xi, where xi is x naught plus I into h. The Euler's formula is given by yn plus 1 equal to yn plus h f of xn comma yn. This is the general formula. Let us now see how we can derive this formula from this equation. To derive Euler's method, first of all, we will consider the first order ordinary differential equation. Consider first order OD dy by dx is equal to f of x comma y with initial condition y at x naught is equal to y naught. Let us take this as equation number 1. Suppose we wish to solve equation 1 for y at xi, where xi is x naught plus I into h. Okay, that means we need to find y of xi. Now equation 1 can be written as dy equal to f of xy dx. Now what we will do, we will integrate both sides between x naught and x1 limits. Integrate both sides between x naught and x1 limits. We get integration x naught to x1 dy equal to integration x naught to x1 f of xy dx. We will get y of x naught to x1 is equal to integration x naught to x1 f of xy dx. This side we will get y of x1 minus y of x naught is equal to integration x naught to x1 f of xy dx. Therefore, we will get y of x1 equal to y of x naught plus integration x naught to x1 f of xy dx. We know that y of x1 is y naught, so we get y of x1 equal to y naught plus integration x naught to x1 f of xy dx. Let us take this as equation number 2. Now in place of f of xy, we will put f of x naught comma y naught. Put f of xy equal to f of x naught y naught in equation 2. We will get y of x1 equal to y naught plus integration x naught to x1 f of x naught y naught dx. If you put x naught y naught in f of xy, it will give a constant term, so it will come out of this integration symbol. Y x1 equal to y naught plus f of x naught y naught integration x naught to x1 dx. So we get y of x1 equal to y naught plus f of x naught comma y naught, and here we will get x, limits are x naught to x1. So y of x1 is equal to y naught plus f of x naught comma y naught x1 minus x naught. Therefore, y of x1 is equal to y naught plus h into f of x naught y naught. Why h? Because h is equal to x1 minus x naught. So this one gives the approximate value of y at x1. Let y x1 equal to y1 be the approximate value of y at x equal to x1. So now we have values for x1 and y1. Now starting with x1, y1 and integrating between x1 and x2, we get the value of y at x equal to x2. We started with x0, y0. We get the value of y at x1. Now if we start with x1, y1, we will get the value of y at x equal to x2. So y of x2 is equal to y1 plus h into f of x1 comma y1, which you can write it as y2 equal to y1 plus h into f of x1 y1. Similarly, we get y3 equal to y2 plus h into f of x2 y2. y4 is equal to y3 plus h into f of x3 y3, and so on. Y of n equal to y of n minus 1 plus h into f of x n minus 1 y n minus 1. In general, we can write yn plus 1 equal to yn plus h of f of x n comma y n, which is the required Euler's formula. So this is how we derive Euler's formula from the first order ordinary differential equation. Now let us solve first order ordinary differential equation using Euler's method. Now look at this problem. Here we need to solve this differential equation dy by dx equal to x square plus y with the initial condition y at x equal to 0 is 1 using Euler's method, and h is also given, that is 0.1. You need to find the value of y at 0.3. Given dy by dx is equal to x square plus y with initial condition y at 0 is equal to 1. Here x naught is 0, y naught is 1 and h is 0.1. Therefore, x1 is equal to x naught plus h, 0 plus 0.1 equal to 0.1. By Euler's formula we have yn plus 1 equal to yn plus h into f of x n comma y n, where n equal to 0, 1, 2, 3 and so on. Now let us find the approximate value of y at x1 using x naught and y naught values. The approximate value of y at x equal to x1, that is 0.1, is given by y1 is equal to y naught plus h into f of x naught comma y naught. Y naught is 1 plus h is 0.1 into f of x naught comma y naught. Since dy by dx is equal to x square plus y, which is f of xy. So this one we can write it as x naught square plus y naught. We get 1 plus 0.1. X naught means 0 square plus y naught means 1. Therefore, y1 is equal to 1.1. Now we have x1, y1 values and we will approximate y for x equal to x2. The approximate value of y at x equal to x2, that is x1 plus h. x1 is 0.1, h is 0.1. This is 0.2 is given by y2 equal to y1 plus h into f of x1 y1. y1 is 1.1 plus h is 0.1. f of x1 y1 we can write it as x1 square plus y1. 1.1 plus 0.1 into x1 is 0.1 whole square plus y1 is 1.1. Therefore, y2 is equal to, if you compute this, you will get 1.2110, which is the y2 value. Now we will use x2 and y2 and we will find the approximate value of y at x3. The approximate value of y at x3. x3 means x2 plus h. x2 is 0.2 plus 0.1, 0.3. So in the equation, it was asked that you need to find the y value for x equal to 0.3. So this is the step where you are getting x3 is equal to 0.3. So if you find y at x3, that is the required answer. So this is given by y3 equal to y2 plus h into f of x2 y2. y2 is 1.2110 plus 0.1 into x2 square plus y2. So you are getting 1.2110 plus 0.1 into 0.2 whole square plus y2 is 1.2110. Therefore, y3 is equal to, if you compute this, you will get 1.3361 or y at 0.3 equal to 1.3361. This is the required answer. Now look at this second problem where we need to use Euler's method to solve for y at x equal to 2. From dy by dx is equal to 3x square plus 1 and the initial condition is given as y at x equal to 1 equal to 2. H is 0.5. Given dy by dx equal to 3x square plus 1 with the initial condition y at 1 equal to 2. Here x naught is 1, y naught is 2 and h is 0.5. Therefore, we can find x1 equal to x naught plus h, where x naught is 1 plus 0.5 equal to 1.5. Now by Euler's formula we have yn plus 1 equal to yn plus h into f of xn comma yn, where n is equal to 0, 1, 2, 3 and so on. Now we will find the approximate value of y at x1. The approximate value of y at x1 equal to 1.5 is given by y1 equal to y naught plus h into f of x naught comma y naught. Here y naught is given as 2 plus h is 0.5 and f of x naught comma y naught. Since dy by dx is equal to 3x square plus 1, which can also be written as f of x comma y. So from here we can write that this is 3x naught square plus 1. 2 plus 0.5 and x naught is given as 1. 3 into 1 square plus 1. Therefore we get 2 plus 0.5 and this is into 3 plus 1, this is 4. 2 plus 0.5 into 4 is 2. Therefore, y at 1.5 is equal to 4. Now let us find the next approximate value. Now we have x1 as 1.5 and y1 as 4. The approximate value of y at x2 equal to x1 plus h. We know that x1 is 1.5 and h is 0.5. So we get x2 as equal to 2. Since in the question it was asked that we need to find the value of y at x equal to 2. So this is the step where we will get y at x equal to 2 is given by y2 equal to y1 plus h into f of x1 y1. Now we know that y1 is 4 plus h is 0.5 and f of x1 comma y1 we can write it as 3x1 square plus 1. 4 plus 0.5 into 3 into x1. x1 means 1.5 square plus 1. If you compute this value in calculator, you will get 7.875. Therefore, y at 2 equal to 7.875. which is the required answer. So this is how we use Euler's formula to find the numerical solution of first order ordinary differential equations. Thank you.